terms of the this option, the thing I would be careful about is that you have to check with whatever programs you're applying to make sure to see what they will take. If you're just fulfilling like a degree requirement, then it should be fine to have a passing grade. But if you are applying to a limited enrollment program, a graduate program, something like that, they may require that you have a grade in this class. So that may not be a good option for you. So let me know if you have questions about that. We're supposed to get the official details on that today sometime. And as soon as I get the details on that flexible grading, I will let you know on Blackboard. Also, thank you for filling out the poll for office hours, those of you who did. I'm always available. You can always email me your questions, and I'll get back to you as soon as I can. You can always ask for a particular time to meet one-on-one and talk. That's always fine, and I'll accommodate you as best I can. But some people like to have a specific time where they know they can show up and I'll be there, and they can count on that time. So I want to have a couple times a week that are just set, and then beyond that, I'll always be available for other times as you need. All right. So are there any questions or other issues that you want to talk about before we get started? Okay, I'll take that as a no. So we'll get going here. This will still be saved in that notes directory, so you can if you can't, like if your connection slows down or if my connection slows down and you can't see the writing, you can pull it up in that folder so that you can have a local copy whenever I save it. All right, so on to determining whether molecules are the same, enantiomers, diastereomers, constitutional isomers, or not related. So this one was a little bit tougher as a take-home activity because you didn't have models to deal with. So something like this is, you really had to think about it. The as usual, the best way to do this is to put it in some form where you can really clearly and easily tell whether they're the same or not. So when they're written in totally different forms like that, you don't want to just leave them in there. You want to rewrite them. So in this case, I always think the flatter version of it is easier to see for this. So I'm going to convert this one to that flat version just as is. So I'm going to recognize that this one is down and this one is up. And so if I draw that directly, like here, so that means my up is going to be here and my down is going to be there. Right? So then looking at that, if I just rotate this, whatever that is, about 120 degrees, I guess, you can see that these are very clearly the same. Right. So this one, if you just twist it over, this one becomes here, and this one becomes down here. All right. So then for the next one, we've got two that look sort of similar, but these are actually going to be quite different. And the key here, the way that you can tell that is there's no stereochemistry here. This structure only has one stereocenter, whereas this one has two. So that tells us that these are definitely going to be something pretty different here, because we've got an sp2 carbon here, and with the bromine, and these bromines are both on sp3 carbons. So these are quite different, and these are actually constitutional isomers. The other way that we can tell that is from the names. So this one would be a 1,3-dibromo cyclohexene. And this one, because of the priority rules, would be, actually we go the other way, but No, I was right the first time. Sorry. So this would be like a 3,5 dibromo cyclohexene. So even without thinking about the stereochemistry, we can tell that these are going to have different names and therefore going to be constitutional isomers. Okay. These two are totally unrelated. The reason that we know that, even though they look fairly similar, is they have totally different molecular. It's going to be C6H10Cl2, and this one is C5H8Cl2. So totally different numbers of carbons, unrelated structures. All right. And then over here, this one is a little bit trickier. They look kind of like mirror images, but they are not mirror images because of the symmetry here. These are actually mesostructures. They have that bilateral symmetry. And that means that if you try to reflect one of these into the other, you can always kind of turn it around and see that it's the same thing. And you can actually see that if you just were to rotate this 180 degrees, yeah, 180 degrees, sorry, then you can see that these are going to be the same. So these are the same. Okay, and as usual with these, just like if we were doing an exam in class, look over the exam that I sent back to you, and if it is different, or if I graded something wrong, or if I added something wrong, whatever, make sure you let me know so I can give you the points that you deserve. Okay, this mechanism, this is a tough mechanism. This is actually one from the homework. So if you've done the homework, you saw this before, and I could tell on some of your exams, either you probably did that before or you looked it up while you're doing the exam, which either way was great. Those of you who just sort of tried to figure something out on your own, that was also great. As long as you made mechanistic sense with what you were doing, like based on the mechanisms that we've already seen, I gave you credit for that attempt and for what you did. If you did stuff that was more like clearly wrong, then I couldn't really give you credit for that. But without even thinking about the weird thing that's going on, which is that this 4-membered ring is turning into a 5-membered ring, we can see that at first it really just looks, if we ignore the product for a second and just look at this part, it looks like a typical alkene addition. So we've got an alkene and we're adding water. So what I might do here, if I was trying to figure this out without any references or anything like that, is I would just sort of first draw that mechanism that we know. So I would go, okay, here's my alkene, and I know that my first step is to grab hydrogen. When I grab hydrogen, I end up with this carbocation and water. Water attacks, and we would get this product. So this is not the answer, but I want to kind of get there eventually. This is how I would think about a problem like this. So for our final step, we're going to deprotonate. And get this final product. All right, so that's like the typical acid catalyzed water addition mechanism. Okay, and it's okay to look this stuff up. Remember, this class now, all the assessments are going to be take home. So if you need to look up a mechanism, look up a mechanism. That's fine. But you can also expect that there's going to be more problems like this, where the mechanism is not exactly what we've done before, and you need to think about something else that's happening. So the key to the something else that's happening then is this step right here. We have a secondary carbocation that is next to a potential tertiary site. And so whenever we see that, we talked about that in class, that when you see that possibility, you need to be on the lookout for that carbocation shift. So for the idea that it's not actually the carbocation that shifts, it's other stuff, either hydrogen or carbon that shifts. And that's going to be the key to getting to this unusual let's see if I can fix here. Okay. So what we would do here, I'm going to erase some of this stuff just so I have some room. Instead of having the water attacking there, we're going to recognize that in this case, there's a hydrogen here, and the way that we shift carbocations is not by drawing an arrow showing the cation shifting, because a cation isn't a thing. We're going to show the hydrogen shifting there over to here, which results then in a carbocation ending up there. This jumps over here. And the result of that is this. The hydrogen, there's now two hydrogens here where there was one. There was one hydrogen here, and now there's two. So now we've got that tertiary carbocation, and now is when we can start thinking, okay, how is this thing going to get from a 4-membered ring to a 5-membered ring? 4-membered rings, remember, back into the Alkene chapter, chapter 3, 4-membered rings are strained because our ideal bond angle is about 110 degrees for a tetrahedral carbon. And a square has 90-degree bond angles. So instead of the angle being where it wants to be, it's going to kind of be squished, and that puts it under strain. So what this then can do is an alkyl shift. So this carbon, instead of being connected to this one, is now going to jump over and be connected to that one. So this bond breaks right here, and this carbon is now connected over there. And that leads to this kind of a structure. So then, the rest of it continues just as the usual mechanism. So we finish it up like this. The way my head here. Okay, like that. That makes sense. So that's tough. That's tough to like figure out totally from first principles. I kind of expected that you would look that up and use the book a little bit to try to figure that out. I also didn't make it worth a whole ton of points because I knew it was going to be tricky. Questions about that one? Pretty good. Okay. So next, we're looking for a energy diagram. To draw a proper energy diagram, we need to know the number of steps. Now, I didn't necessarily expect you to know if this would be exothermic or endothermic for this particular reaction. either of those would be okay, although you could have looked up a very similar reaction in the book and then noticed it. But the important thing is that we know that there are two steps because of the carbocation intermediate. We know that the first step is the slowest, is the rate determining step. So that given that, we should have something like this. Right? So we've got reactants, products. Here's our carbocation intermediate. And then we can see that our first activation energy is bigger than our second activation energy. Questions? Good? All right. Drawing amoxicillin where every stereocenter is in the S configuration. So this one's a little tricky, and it ended up even being a little bit going through it. So I'll show you how I graded this. So first of all, how do you do something like this? As we've talked about before, whenever we want to specify a stereocenter in one particular configuration, I think the easiest way to do it is to just first draw it out somehow. Check the configuration, and then anything that's wrong, just flip it. Pencils are really helpful for this. So I'm just going to redraw this, and I'm going to randomly pick some configurations. So we first have to recognize where the stereocenters are. There are 4 in this molecule, so here, 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 and there. This one is not a stereocenter because it has 2 methyl groups, so those 2 are identical. Just draw this thing out here. Okay, so to specify some stereocenters, so I'm going to say, like, let's just do a wedge here. Remember, this is not the answer yet. I'm just starting somewhere. So let's put a wedge on that one. Let's put a wedge on this one. I don't know why that's doing that. Okay. We'll put a wedge on that one. We will put a wedge on this one. And we'll put a wedge on this one. So we're basically putting all the hydrogens in the back. All right, so then we can check our priorities here. And I'll show you where this gets tricky. So this one, nitrogen is priority 1. The carbon connected to the oxygen is priority 2. And the carbons connected to other carbons is priority 3. So that makes an R, the way that we've got that. So that means that I have to switch this. And then that becomes an S. Okay, moving on to this one. The nitrogen, again, is going to be the first priority. And then we have a double bond to an oxygen, a carbon with a double bond to an oxygen versus a carbon bonded to a sulfur. And so in this case, based on the rules, the sulfur actually gets the priority, even though that's a double bond to the oxygen, because 2 oxygens is still not equal to 1 sulfur. I believe that's true. And anyway, this one's connected to a nitrogen as well. So you got basically nitrogen, sulfur, hydrogen versus oxygen, oxygen, nitrogen. And so nitrogen, sulfur, hydrogen wins in that case. So this is second priority. This is third priority. That I think is a little too difficult. I didn't anticipate that. So whatever you did on that one, I didn't really count it. But this one should be a dash then also, because we want that to be S, and the way we've got it set up right now is R. Okay, moving on to this one then. Sulfur gets first priority, nitrogen second priority, carbon third priority. Again, we've got that one in the wrong, we've got that one switched because that looks like R right now. So we want to switch that one to the dash. And then over here, first priority, I gotta switch colors again so it doesn't get too confusing. First priority is the nitrogen, right, coming off of this one. Then we've got a carbon connected to some carbons, 2 carbons and a sulfur, versus a carbon connected to 3 oxygens. So again, that one takes priority. And that one is S as is. So that's actually what it should be, I believe. Again, those priorities were a little bit difficult to assign. So when I looked at as long as I could tell that you were assigning priorities in a way that made sense, and you got kind of the like this one, then you got full credit, even if you switched some of these middle ones. So let me know if you don't think I graded that right for your particular exam. Okay, everybody's quiet this morning. Any questions? Everybody good? Okay. This thing here. So then, oh, sorry. Go ahead. Kind of out of order. But the internet says, like the whole internet, that if a tertiary substrate becomes an alkene, then it's always E1. E2 can only happen if the leaving group is axial. Sort of. Sort of. So yes, it's true. We didn't talk about this, but since you bring it up, E2 actually has to happen in this particular geometry. So the E2 base has to take the hydrogen that is anti and also axial, and it actually has to go in that geometry. So if there's no sorry, lost my thought for a second. It has to go in this geometry. So if the leaving group can't be axial, then it cannot be E2. It has to go E1. Additionally, so for your other question, a tertiary substrate becomes an alkene, then it's always E1. I don't think that's true. It depends on the conditions. It's true that a tertiary substrate like this, if it's in like a protic solvent, for instance, it's going to, that leaving group is going to leave fairly readily, and you're likely going to form carbocations. And as long as that can be relatively stabilized in solution, then yeah, then it's going to be E1. But if you have conditions where you have a really strong base, you have an aprotic solvent, then you can still, I believe, I'm pretty sure that you can still favor the E2 mechanism in that process. Is that in reference to a particular question, to like one of the ones up here from before?
No, it was actually from the quiz, number 10.
Oh, from quiz 8?
Yeah.
Um, let me pull that up here. Yes. So you're saying like for the second one?
Yeah.
Yeah. Um, so yes, I think that E1 would probably would dominate here. The axial leaving group thing doesn't apply here because that's only talking about cyclic structures, cyclohexane in particular.
Yeah, that one was for question 7, I think.
Oh, okay. So you mean this one here with the chlorine and the cyclohexane?
Yeah, I think I put E2 for that one.
So these are all eliminate. This is not asking which elimination. This is saying in general, when these things form elimination, what are the products that are going to be formed? So in this case, there are two possible elimination products. I guess, yeah, but definitely the major product is going to be this one, or with the double bond here, it's the same thing. And then you could potentially have an E2 elimination product here with a really strong base, but this is definitely going to be the major products. So for this particular question, what products are formed from all elimination reactions? You've got, oops, sorry, sideways. So if we're looking at all possible elimination products, we see that these are both possible elimination products, but this one is favored. But the axial versus equatorial thing doesn't really apply to this. It's not something we've talked about in this class. All right, does that help? Does that make sense?
Yeah, it's what I had, but maybe I just didn't understand the question more so. That it was asking me to decide between E1 or E2.
Okay, yeah, this one is asking those things. This other one is not. This one's just saying general beta, like all possible beta eliminations. The reason I like this question, this is a good preparation for understanding these reactions, because look at a substrate, especially something like this one that has various different possibilities, you want to keep in your mind what are all the different possible ways that this thing can eliminate. So it can eliminate down here, over here, over here. You can even have a carbocation shift and have it eliminating, which actually is symmetric, so it ends up being the same thing. So you want to like think about all those different possibilities. So then you can use your skills to say, oh, okay, well, now that I know all the possibilities, now I can pick that this one's going to be favored. Because if you don't think about all of them, you might be missing one that's actually favored. Oh, while we're on the quiz here, so a couple people have asked for a couple days extensions on this quiz, and as is the theme with all of this business going on, I'm going to be flexible with that. So that's why we're not going over the quiz today. But there is no quiz for this week going into next week because we haven't really talked about anything new yet. So next week will be the next quiz. I've also posted a place for you to turn in your lab notebooks. So whenever you get a chance, from now until basically the end of the semester, please scan in the pages of your lab notebook and turn it in there, and then I can grade them and give you credit for it. We had a department meeting yesterday about what to do with labs, and in most cases, we did at least 2/3 of the labs anyway, so we're just going to say that the labs are done, and we're not going to try to do extra, like, fake labs for this class. The exception to that is if you need more lab points, like if you missed some labs, if your notebook did not go well, and you need more points in that particular category of lab notebooks, then I can find something for you to do to get those. But I think for most people you should be okay. Just turn in what you've got when you've got it, and then I can give you points for that. I've also put in some more detailed directions and a place to turn in your annotated bibliography, which will be due in 2 weeks. Okay, we're really.
So what does that mean for the rest of our time where we would normally have lab?
Sorry, can you repeat that? I didn't catch that.
So what happens to like the rest of the time when we would normally have lab?
I mean, nothing. So our classes are all supposed to be converting to an asynchronous format, which means that you should be able to do your work at whatever time, when you can do it. So you don't have to be here at a particular time. I'm going to keep doing this way because I think it's working well, and as long as I can record it, then people can join in whatever. So there isn't additional lab work to do at this point. But Nicole asks, if we didn't get full points in the last lab notebook, is there a way to get some of those points back or no? So there's not a way to get the points back from what you've already done, but if you want more, if you find that after all the lab notebook stuff is done, that you still need more lab points, that you want to do additional labs, then I will find a way to have a sort of an offline lab where you watch some videos of somebody doing a lab, and then you write about the results of that. That will be similar to what we would have planned for our last 3 labs. So let me know if you want to do that, and I can post that. It's not extra credit exactly, but if you've lost a significant number of lab points and you need more points, then that would count toward that. Yeah, there are some fun online labs. There are some ones that actually have manipulatives where you like drag the flask over and like do stuff. Yeah. So yeah, they do have that kind of stuff. There isn't a whole lot in the organic realm really, but we can definitely find things. A lot of what the bigger universities did, they had TAs come in and perform the labs and make mistakes and on video, and then the students are asked to like evaluate what they're doing and write about what they did right or wrong, stuff like that. So we could pull some of those up and do that kind of thing too. Okay, oh, this is the quiz again. All right, let's go back to the exam. Okay, so this last part was difficult, but it's one of the most important parts of organic chemistry, even for those of you who have no interest in becoming organic chemists. But it's the thing that really makes you think critically, that makes you try to figure out this problem almost like a puzzle. We're going to be doing more of these, and as we learn more and more reactions, we kind of add to our toolbox of what types of reactions we can use to do these transformations. And by the end of the class, we'll be able to actually build some pretty significantly big, complicated molecules with all the reactions that we know. So we're going to keep doing this. And this is a good start based on the reactions that we know. So I want to go through some of the strategies here and how we figure some of these out. And I'm going to jump around a little bit because the first one is not the easiest one. It's not the most straightforward. So I want to start with the second one, which probably is the most straightforward. As we talked about before, the first thing you want to do with these types of problems is always look at the starting material, look at the product, and try to identify what's happened. Like what kinds of things have come in, what kinds of things have broken off, what kinds of things are staying the same. And then from there, we're going to work backwards to try to figure out how these various things were attached. So in this one, I can see I'm starting with a 2-carbon alkyne, right, acetylene. And I'm ending with a 1, 2, 3, 4, 5, 6-carbon alkyne. But it's still an alkyne. So I would say this one is fairly easy to see that that alkyne stays the same throughout the reaction. Now that all of this stuff is a little bit trial and error. Like it could be that once we start getting into it, we realize that we don't actually want to keep that alkene or alkyne the way it is. But for a first guess, it makes sense to assume that that's staying the same. So that means we're adding 2 parts. We're adding 2 carbons here, and we're adding 2 carbons here. And that is pretty much it for this reaction. We can see that we start with this, we add 2 carbons. So then we want to ask ourselves, how do we add carbons to an alkyne? And as we've discussed, one of the reactions, the only reaction that we've learned so far that makes carbon-carbon bonds is to take an alkyne, deprotonate it with a strong amide base, and then add the carbon with some sort of a leaving group in an SN2 type mechanism. So that looks like this. We start with the alkyne. We protonate it. And we add 2 carbons with some sort of a leaving group. And then we know that we can do an SN2 type mechanism where the acetylide displaces the bromide and ends up being connected there. And so that's kind of like the first half. And then we do it again to get the other side on there, the other 2 carbons on there. So when we list this then over here, we would say first, let's deprotonate the acetylene. Then let's add our bromoethane. You know, we could use line structures if you want to. Same thing. And then let's do it again to do the other side. Like that. So questions about that? Issues? Okay, so now let's jump back up into this one. We don't have, so again, we're going to start by identifying what's stayed the same and what's changed. In this case, we start with a 4-carbon alkene, and we end with a 4-carbon alkane. So, well, I mean, there's another carbon here, but with something else on there. But we can assume then that this thing is mostly staying the same. Sorry, my phone's ringing. We can assume that this thing's basically staying the same. And we're adding this, SCH3. Now, the reason this isn't just a one-step transformation is we haven't learned any kind of reaction where we can simply add SCH3 and H to an alkene, or to an alkene, because we're adding SCH3 to carbon 2 and we're adding a hydrogen to carbon 1. So we don't know that. That's not a reaction that we've talked about. Where we have seen these types of groups is in SN2 type chemistry. We know that this is a really good nucleophile that can displace something else. So we know that we can make these from some kind of SN2 substrate because it's a good nucleophile, and we, with some polar aprotic solvent or whatever. You could also use like an ion form of this, like something like that, be even a stronger nucleophile. So whatever nucleophile you choose, we can use SN2 type chemistry to displace it like that. We want to make sure we're in really good SN2 conditions because we don't want to, well, I guess for this one, SN, there's no stereochemistry to worry about or whatever. So yeah, anything like that is fine. But we can't just go directly from the alkene to this. We have to go through the intermediate that has some kind of SN2 good leaving group. So our first step is going to be getting from the alkene to something with a leaving group. And we know we can do that just by adding HBr. So our first step is getting that leaving group onto the alkyl chain and then displacing it with SN2 conditions. So question, how do you know what step goes on the top and which ones go on the bottom of the arrow? It doesn't matter. It doesn't matter. The thing that's important is that subsequent steps that are done one after the other need to be numbered. And things that are done at the same time are not numbered. So if you have a situation where you have like a reagent, like a nucleophile, and a solvent, the convention is you put the nucleophile on the top, you put the solvent on the bottom, if that's all there is. But it doesn't actually matter. You can put anything anywhere you want. Usually the actual reagent is listed first, and then things like solvents, temperatures, time are listed after that. But it doesn't matter what goes on top or the bottom. I could have just written 1 HBr, 2 the other stuff, all on top of the arrow too, or on the bottom of the arrow. Okay, moving on. So here we have a few more changes. We're not adding any carbons. We've got a 5-carbon thing here. Oh, excuse me. Here. And then, thanks. And then we're adding some bromine and some hydrogen, don't forget. They're not shown, but there's a couple hydrogens here that weren't here before. So we got to add 2 hydrogens and 2 bromines. So we can't just add bromine directly to the alkyne because we'd get a bunch of extra bromines on there. We didn't even talk about brominating alkynes. We talked about brominating alkenes. So again, let's work backwards. These always work better, even though it's hard to necessarily think. It's hard to think that way at first, but it works better if you can think backwards with these. So we say, like, just in one step, what could directly make this? And the answer is we could directly make that from an alkene if we reacted it with bromine. The book would also specify a solvent like CH2Cl2, but the important thing is the bromine. So we've got an alkene, we can brominate it and get this. So that answers that first question. What do we make this from? We make this from an alkene. So then the second question is, what can we make the alkene from that gets us closer to the beginning? And in this case, we can get directly there in just one more step, because we know that we can make alkenes from alkynes by reducing them with that Lindlar's catalyst. So we'll take hydrogen, Lindlar's catalyst, and that's our full transformation. So our first step is the reduction to the alkene, and then the second step is the bromination. Right, questions about that? It is important here that you use the correct reduction. If you simply said palladium or carbon, that's not quite right, because that would reduce all the way down to the alkane. And once you've got an alkane, you're kind of stuck. You can't brominate that in this particular way. All right, and then the last one, this, again, we start with an alkyne, and we end with an alkane, an alcohol actually, and we haven't added any carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we don't have to do any of that substitution type stuff. But we do have to think, how do we add an OH? And we can't add that directly to an alkyne. So thinking like from here, you get stuck. It's like doing a maze, like, you know, drawing the maze. It's a lot easier to do a maze if you start from the end, because chances are there's a lot of different forks kind of coming off from the beginning, but the end only has one route back to the beginning, probably, or fewer routes. So that's the idea here, is that if you start from the end, you're not going to kind of get lost off on the wrong fork and end up on a path that doesn't lead you to the answer. So in this case, the way to do that is to say, what do we make an alcohol from? Where does this come from? And there's various choices, but for us, the main choice right now, the thing that we've seen the most of, is to make alcohols by hydrating alkenes. So we take an alkene like this, and we use acid catalyzed hydration, or hydroboration oxidation if you prefer for some reason, but this is much easier, to take an alkene and turn it into an alcohol. So we're not thinking about the beginning yet. We're just saying, where does that alcohol come from? It comes from the hydration of an alkene. So then we can go back again and say, all right, well, what do we make alkenes from? Well, we can make alkenes a couple different ways. We can make them from elimination, but that's not really helpful in this point in this case, because, you know, we don't have that yet. But another way that we can make them is from alkynes, just like the previous question. So we can reduce an alkyne to an alkene with Lindlar's catalyst. And that should take care of it for us. So again, we're first going to reduce, and then we're going to hydrate. All right. And that was the first exam. Concerns about that? All right, I know I have one more quiz, well, two now, to get into Blackboard, but the exam was in the wrong category at first because it was set up as an assignment because you submitted it. So I changed that. So your overall weighted average does now take both exams into account. Check that your points are up correctly, especially because I graded these digitally. I could have missed something here and there depending on the scan. All right, so a question about tutoring. Tutoring appointments are limited to 30 minutes of one-on-one time. You just gotta hope someone else didn't book your day of the week or time, or the tutor you like. Yeah, so you've got to, how far in advance can you book it? Monday next week. Yeah. Well, yeah, I mean that's not ideal. I guess they're doing what they can, but use me for that. Like maybe you don't like me as much as the tutors. That's fine. I understand that. But I'm here too. So if you want an appointment, let me know if you want to meet sometime, and I will meet you on here, and I can answer your questions. Yeah, if that tutoring's not working great, then let me help you. All right. Other questions, concerns? When do we have to decide until if we want to do pass, fail, or letter grade? I don't know. We're supposed to get the details of that today sometime. Actually, I haven't checked my email. Let me see if I have that. No, I don't have anything yet. So we're supposed to get official um, communication about that soon. My understanding is that yes, no, not all courses will have that option. But my understanding is that you do not have to decide that until the end. It's just another option that we have when we enter your grades at the end. Courses that have that are associated with particular certifications, like nursing courses and things like that, are probably not going to have that option because they have to have the grade in order to count toward the certification. Additionally, you're going to need to check on wherever you're planning to go after this to make sure that it's okay to have that option. So like if this is just counting as a general education requirement or a lab science or something like that, the pass grade is probably fine. But if you need this class as a prerequisite to like a nursing program or a graduate program or something, you have to check with them because they may not accept that pass grade as fulfilling your requirement. Yeah, so I'll let you know as soon as I find out more about that. Okay. We've only got about 15 minutes left, so we're not going to do a whole bunch of new stuff, but I do want to just introduce the next chapter so that you can get started with your homework and get started with studying with that. Maybe if I can get some. Okay, maybe not. All right, we'll just get it. There we go. We got a couple extra pages in here. So we're moving on to chapter 8, which is the chemistry of alcohols and some related structures. Now we've seen alcohols before, things like that, but we haven't talked specifically about naming them. We haven't really talked about reactions of them. We've talked about how to make alcohols. We have a couple different good ways of making alcohols. One would be adding water to alkenes, as we talked about. Another one would be substitution. You can substitute for alkyl halides and put alcohols on there instead. But we haven't talked about what to do once you have an alcohol. How do you turn an alcohol into something else? So we'll be talking about that a little bit this chapter. For today, since we only have about 15 minutes, let's start with just some naming of alcohols. So we'll start even a little bit simpler. Okay. This molecule would be called. Anybody want to take a guess on that one? guesses? Okay, I'll give you a hint. It has 2 carbons. So what do you think it starts with?
Is it methanol?
Yeah, it's ethanol. So 2 carbons is always eth, right? Ethyl, ethane. So this is going to be ethanol. So notice how that word is set up. We've got the ethane from ethane. And now the new part is our alcohol suffix. To show that it's an alcohol, we have, oops, it's in my head here. We have our alcohol suffix. Move out of the way there. There we go. So we should also note, this is the correct way to name this. This is what we would call the IUPAC name. But just because it exists, and you're probably going to see it now and then, there's an older way to name alcohols, which uses the whole word alcohol. So we would call this ethyl alcohol. Same thing, same structure. This is a more versatile name because you can use it for larger structures, and that's why it's the IUPAC name. But if you see this, don't get freaked out. It's the same thing. So that's why, like, when you buy rubbing alcohol in the store, it's usually sold as isopropyl alcohol. This is what we would call in the old name my head away. The old name of this would be isopropyl alcohol. But the better name, or the IUPAC name, is 2-propanol. So we're going to use the number format to indicate where that alcohol is. So if this is a 3-carbon structure, 1, 2, 3, then this would be 2-propanol. All right, so then what do you think this one would be called? Do we want to type in a possible name or just say it if you've got your mic on?
Is it 2-butanol?
It is 2-butanol. Thank you. Yes. Yep. Great. So this would be 2-butanol. All right. Let's look at some other ones. So we can have multiple. There it is. We can have multiple alcohols on a structure as well. So you could have something like this. This one would be, so again, it's a propane-like structure. We've got 3 carbons, and this would be 1, 2, 3 propane triol. So just like with the alkenes, when we had, was my cursor gone? What happened to my cursor? You guys can't see my arrow, can you? All right. That's weird. I can see it on my. Okay, well, I'll just like circle stuff. I was here before. Oh, there it is. Okay. So 1, 2, 3 propane triol. We've got our three. So just like with the alkenes, we had like triene, dienes, and trienes. We can have diols and triols. This one also has an important use in the world. It is known as glycerol, glycerin, or glycerine. Um, those are just common names for the same structure. So um, that's used. You can get that in like drugstores. It's used in a lot of pharmaceuticals. You can make a lot of like flavor extracts and stuff. If you've ever seen alcohol-free flavors and fragrances, they're usually made with glycerol. It's also a byproduct of biodiesel production. But the IUPAC name of that would be 1, 2, 3 propane triol. All right, so please start working through. This is a good opportunity since we kind of slowed down a little bit. Good opportunity to get ahead, to read into chapter 8, and to start looking at alcohols. Remember that these classes are always going to be most useful if you've already heard about this stuff a little bit, and then you come and you have some questions, or we can do some practice problems together. And then I will set up some probably just a couple times a week that are fixed office hours where I'll always be here and you're welcome to drop by. But as I'm stuck at home, I will also have other times. So if you need help, if you're working on the homework, if you're working on the quiz, or whatever, and you need some and you have some questions, let me know. We can find a time and meet up. So stick around if you have any other questions. Otherwise, I will see you Monday, if not before. So thanks, everybody. Yep, have a good day. Bye. Tomorrow, 12:30. Yeah, that should work.